Bismillahirrahmanirrahim. Dear students, today we are going to discuss another method for olefination, that is creation of carbon-carbon double bond, which is known as Sharpless olefination. Basically, this method is olefination from alkyl halides. So we will discuss in detail. The key concepts of today's lecture is the brief introduction to the Sharpless olefination reaction. This introduction was discussed in detail in the last lecture, and here we will have a brief introduction, and then the mechanism of the reaction overall, and then the explanation of mechanism step by step, and then the mechanism for the modification reaction which was given by Greco, and in the end there will be discuss some synthetic applications of this reaction. Sharpless olefination reaction is basically the formation of alkenes from alkyl halides through the formation of selenoxide. The alkyl halide should contain alkyl group or R-alkyl group, not aryl groups. You know alkyl group like ethyl, propyl, etc. And the R-alkyl group mean aromatic ring or aryl ring is attached to alkyl group, and that is attached to the halo group. This group is known as R-alkyl group. So R-alkyl group should be present in the alkyl halides for the formation of alkene. And another condition for this alkyl or R-alkyl group of the alkyl halide is that it should bear some beta hydrogen, because in the last step of this reaction there is elimination reaction. Due to this elimination, alkene is formed, and that elimination require the presence of a beta hydrogen in the alkyl or R-alkyl group. So overall this method is the way of formation of olefins from alkyl or R-alkyl halides. Here you can see the general reaction of this Sharpless olefination method, that alkyl halides are treated with aryl selenide anion. This anion is prepared from selenocyanates, and then this anion reacts with alkyl halides to form selenides. These selenides are oxidized in the presence of hydrogen peroxide in tetrahydrofuran as a solvent, and we get the alkene. Here is the overall mechanism of this reaction. The first step is about the reaction of selenocyanate with sodium borohydride as a reducing agent in ethanol or DMF. DMF means dimethyl formamide, and this reaction produces the selenium oxide, or selenoxide. Yes, you can say selenide anion. This selenide anion reacts with then alkyl halides to produce selenides, which are simply divalent selenium compounds with 2 carbons, and then this selenide is oxidized in tetrahydrofuran to form selenoxide. This selenoxide then goes through beta elimination reaction and is converted into alkene, and you can see here that this alkene is coming from that part of selenoxide which was inserted through alkyl halide. Here is the first step of the mechanism, that is reduction of selenocyanate to selenide anion. Selenocyanate is reduced by sodium borohydride to selenide anion. The name reduction is given because in selenocyanate you can see the oxidation state of selenium, and then you see in the product the selenium is negatively charged, whole negatively charged. It means it has gained electrons, so it has gone through a reduction process. Therefore, it is named as reduction. Sodium borohydride is structure of sodium is shown here, sodium ion and then borohydride ion BH4 minus, and you know that borohydride ion attacks through the sigma electrons, that is one of the hydrogen attacks or acts as a nucleophile in which the sigma electron present between boron and hydrogen, this pair of electron moves towards the hydrogen making it a nucleophile, and this nucleophilic hydrogen attacks on an electrophilic center. And in selenocyanate, the carbon which is attached to partial negatively charged nitrogen or electronegative nitrogen, so it will get a partial positive charge, that is it will be an electrophilic center, and this nucleophile will attack on this electrophilic center. Then this pi bond is broken and it moves towards the nitrogen, and we get an intermediate in which carbon nitrogen contains a double bond, and nitrogen also bears a full negative charge which is counterbalanced by sodium ion. In the next step, this negative charge moves back towards the carbon making it again triple bond, and the bond between carbon and selenium is broken, and both of electrons move towards selenium making it an anion, and we get a byproduct, that is hydrogen cyanide. Here is a question: why nucleophilic hydride which actually attacks through sigma electrons? That is it means that we should not represent here that H minus H hydrogen with a full negative charge, because in actual practice the whole anion moves toward the electrophilic center, that is BH4 minus, and the sigma electron of the BH attacks on the electrophilic center. The question was why nucleophilic hydride attacks carbon instead of selenium, although electronegativity of both is same, that is carbon electronegativity is 2.55 and selenium electronegativity is also 2.55, both have the same electronegativity. Then why this nucleophilic hydrogen is attacked on carbon? The answer is simple, that it is directly attached to an electronegative atom which has created some electron deficiency in electron density, and it has become electrophilic center, and the nucleophilic hydride attacks on it. The other question is why selenide anion is formed so easily? That is the intermediate when this borohydride nucleophile has attacked on the carbon, and we get a double bond and a nitrogen with a negative charge, and this negative charge moves back and this carbon selenium bond is broken. But why this bond is easily broken? The question was that why this carbon silicon bond is easily broken, that both of the electrons are moved towards the selenium and making in full negative charge. And this is a simple thing, as you know, phenoxide ion are very stable because the negative charge of oxygen is stabilized by the resonance through the benzene ring, and similar cases here, that this negative charge on selenium is also stabilized by the resonance by the phenyl ring. The second step is the reaction of previously synthesized selenide anion with the alkyl halide. The selenide anion, as it has full negative charge, so it acts as a strong nucleophile, and this attacks on the electrophilic center of the alkyl halide. Electrophilic center mean the carbon, alpha carbon, which is directly attached to halogen, is partial positive charge due to electronegativity of halogen. So this nucleophilic selenide anion attacks on this alpha carbon, and the halo group is removed from this, and we get the selenide. The byproduct with this main product is sodium halide. Here the main thing which should be discussed here, that the solvent used for this step should be a protic solvent. As we have discussed in the first step, there was the possibility of the use of ethanol or DMF, because there was no properly nucleophile minus full negative charge anion, which can be protonated by a proton, and the nucleophilicity of that anion will be reduced. But here in this case you can see the selenide anion with full negative charge if we use a protic solvent. Protic solvents are the solvent which can donate with a proton to the species present in the reaction mixture. So if we use a protic solvent, it will donate a proton to this anion, and this negative charge will be counterbalanced by that proton, and the nucleophilic character of this anion will be reduced up to much extent. Therefore it is recommended that for this step we should use a protic solvent, the solvents having no ability to donate proton. The examples of such solvents is THF tetrahydrofuran, or DMF dimethyl formamide, or DME dimethoxyethane, etc. And the protic solvents which decrease the rate of reaction due to protonation. The examples of such solvents is ethanol, ETOH, MEOH mean methanol, water, etc. The third step is the oxidation of the previously synthesized selenide to selenoxide. The oxidation here is shown through hydrogen peroxide. The mechanism is discussed for hydrogen peroxide H2O2. Here you can see that there are two lone pair present on selenium, because it is the member of 6 group, and it has 4 electrons in the valence shell as in the form of 2 lone pairs. This lone pair attacks on the oxygen of hydrogen peroxide. Here you can see the structure of H2O2, that is 2 OH groups are attached through a single bond, sigma bond. The lone pair of selenium attacks on the oxygen, and the sigma bond, both of the electron of sigma bond move towards the other OH group, and we get the hydroxide anion, which acts as a nucleophile in the next step, second step. Here as selenium has got 3 bonds, so it is positively charged here. Now the anion, hydroxide anion, attacks on the hydrogen which is partial positive charge, and the sigma electron both moves towards the oxygen, and it gets full negative charge, and we get the selenoxide in the form of this, where selenium is with positive charge and oxygen is with negative charge. Overall the molecule is neutral because positive and negative charges are counterbalanced with each other. Here is the similar thing as we have discussed in the last step, that a protic solvent is required in this step also, because we have hydroxide ion which is acting as a nucleophile. If there is protonation, then this nucleophilic step will be hindered, and the conversion to selenoxide will be decreased too much. Here is a question that oxygen is not an electron deficient species because it has lone pairs. Then why lone pairs are attacking from selenium to oxygen? And then when we are showing attack from the lone pair of oxygen towards the lone pair of selenium towards the oxygen, although oxygen has 2 lone pairs, it is not looking to be an electron deficient species. But we know if we compare the nucleophilicity of both oxygen and selenium, then selenium is at 3rd position in the group. That it means it is greater in size as compared to oxygen, and due to large size its lone pairs are too much away from the nuclear attraction, and they are acting as a very strong nucleophile. So selenium is a strong nucleophile as compared to that of oxygen, so it will act as a nucleophile and will attack on the oxygen of the hydrogen peroxide, and this attack is also stabilized by the other oxygen, which easily removes the two electrons of sigma electrons and makes the hydroxide ion. So this attack is much favorable. Secondly, what will be the charge on selenoxide? As we have discussed that both there are positive and negative charges present in the species, so overall it is neutral species. And this bond also, which is shown by plus and minus, this bond can also be shown through double bond or through coordinate covalent bond. Next, why selenium oxide is shown in the form of dipolar bond? I have answered this, that it is actually a coordinate covalent bond. That is, the one lone pair of selenium can coordinate with the oxygen if we draw the liver structure of this compound. As we have discussed different oxidizing agents in the last lecture, including H2O2, ozone, NCPBA, metachloroperoxybenzoic acid, oxaziridine, and sodium periodate. In addition to these oxidizing agents, there are some also methods or ways in which the selenides are converted into selenoxide. One of these methods is that first the halogenation of the selenide with chlorine or bromine, and then the alkaline hydrolysis or the treatment with silver oxide to get selenium oxide from these selenides. And the yields of these this conversion is found to be reliable, or you can see prominent one. Second way is the treatment of the selenide with N-bromosuccinimide NBS or N-chlorosuccinimide NCS or tertiary butyl hypochlorite, and then the hydrolysis of these reagents we get the selenoxide or directly alkene, and also in very good yield. The last way is that different oxidants like N2O4, nitrogen dioxide, TTN, that is also known as tartronate, TTN, and chromium oxide, chromium trioxide. These have been used as an effective oxidizing agents for the conversion of selenide into selenoxide. Here structures given for N-bromosuccinimide NBS, N-chlorosuccinimide NCS, tertiary butyl hypochlorite, and then tartronate, TTN, also known as 2-hydroxypropane dioate. It is in the salt form. Here discussion can be made for the asymmetric oxidation of selenide to selenoxide. There is a difficulty in preparing optically active selenoxides, and this difficulty can be regarded to the configurational instability of these optically active selenides, and so we get achiral hydrates even in the presence of traces of water, moisture from air, etc. The initial selective oxidation of alkyl aryl selenides with oxaziridine has been achieved, and this initial selectivity can be attributed to its aprotic nature, and also the formation of this initio selective product is about 91 to 95%. Initio selective means that we get one of the enantiomer selectively in most percentage or most ratio. The negative oxaziridine and positive oxaziridine affords the S and R configurational selenoxides respectively. This conversion is enantioselective. Selective. One of the point which should be kept in mind for using these reactions, that the moisture and trace amount of acids in the solvents is too much negative effect on this reaction. Here you can see the reaction also in which selenide is treated with negative oxaziridine or positive oxaziridine in the presence of chloroform, and we get the R isomer or S isomer, R isomer from negative oxaziridine and S isomer R isomer from positive oxaziridine and S isomer from negative oxaziridine. And you already know about the configuration of a molecule which is nominated through R configuration or S configuration, that is clockwise or anti-clockwise arrangement of the molecules groups attached to a quad 4 bond forming atom. The last step of this reaction is olefin formation. The selene oxide is gone through beta elimination using a cyclic transition state, and it forms alkene. This elimination reaction, also called Greco-Sharpless elimination, an example of syn. It is an example of syn elimination. Syn means the elimination from the same side, and as it is a syn elimination from the same side, so there are more chances that the products are Z alkene, that is the alkene having the groups on same side. The effects of different things have been studied for this reaction, this step, that the presence of protic solvent has a negative effect on the rate of elimination because it can affect these charges, and so aprotic solvents are recommended here. Also the presence of chloro electron withdrawing group, chloro halo group, or phenyl at alpha or beta position of the species which has come from alkyl halide. This group had come from alkyl halide, so as it has come from alkyl halide, the alpha or beta position may contain chloro or phenyl or substituted phenyl, and alpha position may contain alkyl group. All these things have positive effect on the rate of elimination of this selenoxide to form alkene, but the presence of alkyl or alkoxy group at beta position decreases the rate of the reaction. This increase in rate is due to favoring the charge distribution which is moving through the cyclic transition state, and the decrease in rate is the decrease in this charge distribution, which is actually the basic reason for the cyclic transition state and the formation of alkene. Some of the side reactions have been known for this. The last step of alkene formation from selene oxide. This reaction is also known as selenoxide elimination. One of the side reaction is seleno-pumiral reaction in acidic conditions. In acidic condition, the protonation of selenoxide intermediate occurs, and then this followed by the elimination of hydroxide, and then moved to hydrolysis, and we get the formation of a carbonyl compound. Here you can see the reaction in which after protonation the selenium oxide is converted into selenic acid, and then after the removal of water we get a double bond between selenium and carbon, and on hydrolysis we get the removal of this alkyl selenide group, and we get the products having carbonyl group. The second side reaction regarding this step, that is selenoxide elimination, is the reagents, that is the which where the aldehydes or ketones are ready. Selenization of the intermediate selenoxide occurs. Selenization means that is the addition of another selenyl group, aryl selenyl group on the carbon which is already attached to the selenium atom through the formation of selenium oxide. The tertiary selenoxides which are unable to undergo enolization do not react further with selenium electrophiles. Here is the example reaction overall of this side reaction, that a carbonyl containing compound is converted into selenoxide oxide, and this selenoxide moves towards through to enolization, that is formation of a double bond NaOH, and then again reaction with another molecule of phenyl selenide, and we get the product in which this carbon which is at alpha position to carbonyl is directly attached to two selenium atom, one in the form of simply selenide and other in the form of selenium oxide. And after the removal of selenoxide in the form of selenic acid, we get the alkene carbon double bond, but along with the presence of selenide moiety, that is the resulting alkene bears alkyl selenide functionality in it also. Another side reactions for the selenoxide elimination is for allylic selenides. If we are dealing with the allylic selenides, the oxidation does not lead to the conjugated dienes, which is the normal case. Rather than we get the formation of an allylic alcohols which moves through the formation of selenic esters. The selenic esters are formed from selenoxides through 2,3 sigma tropic rearrangement. Here you can see the reaction. First the allylic selenide is oxidized to selenium oxide, and this selenium oxide does not move towards the conjugated system of diene through the formation of selenic acid, selenic acid. Instead it moves towards the formation of selenic esters, and which on reaction with water gives alcohol with the removal of selenide, or you can say selene. Here is the question for to explain is that first, why it is called 2,3 sigma tropic rearrangement. You know about the sigma tropic rearrangement reactions. Here you can see the old bond breaking, which is a selenium carbon bond. The old bond, though both sides of the old bond are named are numbered 1, that is selenium is number 1 and this carbon is also number 1 to which selenium is attached. Now if you number selenium 1, then the oxygen get the number 2, and if we move from the carbon side which is number 1, then the second carbon which is a double bonded carbon is 2, and the third which is also double bonded carbon is 3. The oxygen has attached on this carbon, double bonded carbon number 3. So therefore this is known as 2,3 sigma tropic rearrangement. 2 position, 2 number of oxygen from selenium and 3 number of this carbon from the number 1 carbon, and there is bond formation between the double bond between selenium and oxygen moves towards this third carbon, and the double bond between carbon carbon moves towards the next bond, and we get the breakage of carbon selenium bond. To get the selenic esters. The selenic ester, here is the question why this is named as ester. Although we know that an ester is basically a carbonyl compound which has oxygen attached to it, is called ester, but this is called selenic ester. It is the same thing as we have discussed earlier, that this RSEOH here in this reaction is known as selenic acid, acting as an acid, selenic acid, and when the hydrogen of this OH group is removed by a carbon, then this will name as selenic ester, and this selenic ester on hydrolysis gives the alcohol product, and so this is another side reaction of this selenoxide elimination. This is the modification of Greco given by Greco for the Sharpless olefination. The basic difference between this modification and the original reaction is the first and second step. That is, the in case of Sharpless olefination, as we have discussed, that it used selenocyanate, which were converted into selenide anion first step, and in second step selenide anion reacted with alkyl halide to form selenides. But Greco used alcohols instead of alkyl halides. Here you can see the mechanism. First, trialkyl phosphine, here is tributyl phosphine, acts as a nucleophile and attacks on the selenium, and the cyano group removes as a cyanide ion. In the next step, that the lone pair of oxygen from alcohol attacks on this phosphorus, which is bearing here positive charge, and becomes the electrophilic center, and the sigma bond present between phosphorus and selenium is broken, and selenide anion is produced. This adduct of phosphine and alcohol is attacked by cyanoid as a nucleophile, which was produced in the first step. This cyanide ion attacks on the hydrogen and abstracts it in the form of HCN, which is a very stable compound, and the sigma electron between oxygen and hydrogen moves towards oxygen, and the positive charge oxygen is omitted. Now the selenide anion, which was produced in the last step, acting as a nucleophile, attacks on the carbon adjacent to this oxygen, or you can say alpha carbon adjacent to this oxygen, and makes the selenide with the side product of tributyl phosphine oxide or tributyl oxophosphorane. In the next step are the similar as we have discussed for the previous reaction, that hydrogen peroxide acts as an oxidizing agent, selenium attacks on the oxygen, hydroxide ion is produced, hydroxide ion in return attacks on the hydrogen, making water, and sigma electron moves towards the oxygen, making it negatively charged. This is called selenoxide. This selenoxide goes through a cyclic transition state in which oxygen attacks on the hydrogen, and the sigma electron between carbon and hydrogen moves towards the alpha and beta carbon, and the sigma electron between alpha and carbon and selenium moves towards the selenium, and we get selenium alcohol, or you can say selenium with OH group, and the as a byproduct, and the main product is the formation of alkene. Here are some questions as we have discussed in the last. First question is this: phosphorus bears lone pair, it is nucleophilic. Okay, selenium bears lone pair, it is also nucleophile, can act as nucleophile. And if you say compare the electronegativity, then the electronegativity of selenium is greater, 2.55, but that of phosphorus is less, as 2.15. Second point is that the selenium size of selenium is greater as compared to that of phosphorus. So selenium should act as a stronger nucleophile due to large size, and phosphorus should be a weak nucleophile as compared to that. But you can compare the first we have discussed the electronegativity, that selenium is more electronegative as compared to phosphorus. And second reason for the phosphorus to be acting as a nucleophile can be that the lone pair available on selenium are resonating through the phenyl ring, so they are not too much available for the nucleophile attack as compared to that of phosphine. So therefore trialkyl phosphine acts as a nucleophile as compared to selenium and attacks on the selenium. Second question, that is selenium is more electron deficient or electrophilic center, or the carbon of the cyano group is more electrodeficient species, deficient center. As we have discussed in the first step of the reduction of selenocyanate into selenide anion, the attack by the hydride of tetrahydroborane was on the carbon, not on that of selenium, and therefore carbon should be more electrophilic, and it is also attached to an electronegative center, and the attack should be on carbon instead of selenium. But here is the not case. Why is it so? This thing can be explained keeping in mind that in that step, as we have discussed previously, the formation when the hydride ion attacks on the carbon, and the movement of charges moved, and we get the stable compound HCN, which was stable, so can be formed easily. Number one. Number two, the selenide anion is resonance stabilized, so it should be can be formed easily. So both things favored much to the product side, so the attack on carbon was easily possible. But if here phosphorus attacks on the carbon, the triple bond is C triple bond N is converted into double bond, nitrogen gets the negative charge. When this negative charge comes back and selenide is formed, okay, but the product PBH plus and Cn minus is not too much stabilized product, so it has no thermodynamical stability, therefore it is not formed easily. And in this case phosphorus attacks on the selenium, and we get cyanide ion as a nucleophile. And this second step, this attacks with the reacts with the alcohol and moves towards the product side. This is the modification by Greco for the Sharpless olefination reaction. Here are some synthetic application of this Sharpless olefination reaction. First example is the Greco modification, that alcohol is converted into alkene by the reaction with selenocyanate containing a withdrawing group of nitro, and its yield is 72% for the 3 steps. Second is also an alcohol which reacts with para nitroselenocyanate, and in the presence of trimethyl phosphine tetrahydrofuran at room temperature with 88% yield, we get the selenide, and this selenide is oxidized and gone through the elimination with 77% yield, and we get the alkene. These reactions are also of similar type, that alcohols are converted into alkene, and here you can see in the first reaction there are 2 alcoholic groups. First is here, and second is here. 2 alcohols are present, which are treated with selenocyanate bearing 2 nitrophenyl group, and secondly the selenide is oxidized and cyclized to form the alkenes, and we get alkenes at 2 of the OH groups are converted into alkenes. And this here is overall here is the third 3 hydroxy groups, but 2 are converted into alkene, and this second one is not converted into alkene. And as we discussed, at the position of alpha or beta, the groups present hinders the elimination reaction. So this hindrance causes no reaction at this hydroxy group present in adjacent to methoxy group, but the other 2 hydroxy groups are converted into alkene very easily and has gone through the elimination reaction. Second example is also of an alcohol which is converted into alkene by the reaction of selenocyanate and oxidation, and the yield of both of these reactions is counted to be 90%, and the solvents used are tetrahydrofuran and pyridine. Here are some also examples of this olefination reaction. The first example is the conversion of this biketone into selenide. Although this step is not included in this olefination reaction which we are discussing in today's lecture, the second step is just similar to this reaction which we have discussed today, that this selenide is treated with an oxidizing agent. Here is H2O2 hydrogen peroxide, and which moves towards the selenium oxide from selenide, and then elimination takes place and we get alkene. Similar case is the second one, in which first step is the formation of selenide, and then second step is the reaction of this selenide with ozone, and we get the similar alkene formation after the formation of selenoxide. The third example is the conversion of an anion into selenium oxide, and then the formation of double bond. Here the oxidizing agent used is sodium periodate. 2 reactions are there also discussed this slide. First reaction is the similar as we discussed in the last slide, that the compound is converted into selenide through the use of a selenide chloride, which is not the part of our reaction. And then the second step is just similar as we have discussed, that the selenide is oxidized by sodium periodate to selenium oxide, and that selenium oxide is gone through selenoxide elimination, and we get the product of alkene. In the second step, where Wittig reagent of allyl phosphonium salt is used, which is converted into selenide, and then this selenide reacts with the aldehyde group, and we get the double bond of this carbonyl group. This is purely Wittig reaction, in which phosphonium salts are used in the form of halides to convert carbonyl compounds into alkene. And in the second step, this phenyl selenide compound is oxidized by hydrogen peroxide, and then is converted into alkene through the selenide elimination reaction. Here is a biological reaction that alpha beta unsaturated ketone is converted into selenide by using alkyl selenide, alkyl lithium type compound, and then this selenide is molecule is converted into another molecule through the reaction with the dipeptide of protein, and then this selenide moiety present in this dipeptide is oxidized to selenoxide, and then through selenoxide elimination we get the carbon-carbon double bond. This moiety is then further catalyzed through palladium, and we get the final product of anti-latoxin, which is used as a drug in the medicinal chemistry. Here are last three examples for this reaction, that alcohols. First is alcohol, conversion alcohol into alkene. Second is also a cyclic alcohol, which is converted into cyclic alkene. And the proposed mechanism for this reaction is also shown, which we have already discussed, and the product is cycloalkene. Here you can see that we have not shown examples of starting with alkyl halides, but example with alcohols are mostly present, because it as we have discussed, it has decreased the number of steps, so the efficiency of reaction, the labor of on the reaction has minimized too much. So most of the reactions going on in the market or in the industries are synthetic, for synthetic point of view, or for the olefination. If someone want to olefin, they are using alcohol as a starting material instead of alkyl halide, because it requires more steps and there is more workup, more involvement of different reagents, and this thing reduces the purity, reduces the time, reduces the yield, and so they are not recommended. So this is all about synthetic application. In the end, here are 2 to 3 examples also, which are going from alcohol into alkene, and using the Greco-Sharpless elimination, first with 89% yield, second is 91% yield, and the third reaction is using selenide, which is oxidized to form an alkene, and the starting material of this was also an alcohol. So this is all about today's lecture, and thanks.